this clock stopped working. So naturally, I grabbed a fresh-looking AA battery from my drawer, put it in. And absolutely nothing happened. No ticking, no movement, completely dead. At first, I thought the clock was broken. But then I removed the battery and decided to test it with my multimeter. And what I found was surprising. Take a look at this. The battery is reading around 0.85 volts. Now, a normal AA battery is supposed to provide about 1.5 volts when it's fresh. Most clocks need much more than 0.85 volts to run properly. So according to the meter, this battery should be useless for a clock. And what if there was a simple trick that could make this clock start running again without buying a new battery? It sounds impossible. In fact, when I first heard about it, I didn't believe it either. But after testing it myself, the results were unexpected. For this experiment, I'm going to use a 3.7-volt lithium-ion battery. You can often find these batteries inside old laptop battery packs, power banks, or other rechargeable devices. Before using it, let's check the voltage with the multimeter. And as you can see, the battery is reading around 3.5 volts, so the battery is still holding a good charge. Now here's the problem. If we flip the clock over and look at the specifications on the back, we can see that it requires a single 1.5-volt AA battery. That means this clock was designed to operate at roughly 1.5 volts. In general, most clocks can tolerate a little more than that, but not a huge increase. So a safe operating range is usually somewhere around 1.5 to 2.5 volts. But our lithium-ion battery is producing about 3.5 volts. That's significantly higher than what the clock is designed to handle. If we connect this battery directly to the clock, there's a chance we could damage the clock's electronic circuit, shorten its lifespan, or cause it to behave unpredictably. So connecting it directly is definitely not a good idea. But what if there was a simple way to safely reduce that voltage to a level the clock can use? A method that requires only a few inexpensive components and can give new life to batteries that would otherwise sit unused. In the next step, I'll show you exactly how we're going to make that happen. Now, instead of buying new components, I'm going to use something from old scrap circuit boards. If you look closely at old electronics, like power supplies, radios, or even broken chargers, you'll often find small components called Zener diodes. Now let me show you the purpose of these Zener diodes in this setup. We are going to connect them in series. That means anode to cathode, so they line up in a chain. This gives us a combined voltage drop effect. Now we have one free end as the anode and one free end as the cathode. This is what we will use to control the voltage going into our clock. Let's connect it step by step. First, the anode goes to the positive terminal of the battery. Then the cathode goes to the positive probe of the multimeter. And the battery negative goes directly to the multimeter negative. Now check the reading. The multimeter is showing around 2.6 volts. That's a big drop compared to the original 3.5 volts we measured earlier. And this is exactly the effect of the Zener diodes working together, reducing and stabilizing the voltage to a safer level. So instead of feeding full lithium-ion voltage into the clock, we now have a controlled output. But the real question is, will this be enough to actually bring the clock back to life? Let's test it in the next step. Now it's time to modify the clock itself. Carefully open the back cover using a screwdriver. Be gentle here because most clock casings are made of thin plastic, and you don't want to crack anything while opening it. Once it's open, we need to access the battery terminals inside. For wiring, I'm using old USB cables. You can easily find these from broken chargers or unused cables at home. I'm going to cut 2 wires, ideally one white and one black, just to keep things organized and avoid confusion later. Now we start the soldering process. Take the Zener Diode setup we prepared earlier. We connect the cathode side of the Zener diodes to the positive terminal of the clock. This is important because this is where we want the regulated voltage to enter. Next, we take the white wire and solder it to the anode side of the Zener diode chain. This white wire will act as our main positive input line from the battery. Then we take the black wire and solder it directly to the negative terminal of the clock. At this point, the clock is now wired to accept our regulated power setup. So carefully close the back cover again and tighten the screws using the screwdriver. Make sure nothing is pinched inside before sealing it. Now we need to route the wires outside. We gently pull the white and black wires out through the battery compartment gap. This allows us to connect and disconnect power without opening the clock again. Finally, we connect everything to the battery setup. The white wire goes to the positive terminal of the lithium-ion battery, and the black wire goes to the negative terminal. So this simple setup using a lithium-ion battery and a couple of Zener diodes is enough to power the clock safely without buying a new AA battery. Instead of throwing away batteries or constantly replacing them, we're basically reusing stored energy in a smarter way. This was a very simple experiment, but the result is impressive. It shows how small electronic components can solve everyday problems if you understand how they work. If you found this useful, don't forget to like the video, share it with your friends, and subscribe for more experiments like this. And if you have any questions or want to try this yourself, leave them in the comments section below.